Hi all. Today we discuss the examples of some permutation groups, some important examples. So first we discuss S3. Uh, this S3 is the permutations of on a set of three elements. We start with A. A is equal to 1, 2, 3. A contains three elements. Then once you consider the 1, 1 and 1, 2 functions from A onto itself, then you will get 1, 2, 3, 1, 2, 3. So this is the first element. Next is 1, 2, 3 and 2, 3, 1. Next we have 1, 2, 3, 3, 1, 2, 1, 2, 3, 1, 3, 2, and 1, 2, 3 we have 3, 2, 1. Finally the last one is 1, 2, 3. This is 2, 1, 3. So these are the 6 permutations or 6 1, 1, 1, 2 functions from A onto itself. So this form a group called S3. Okay, these are the elements of S3 along with the binary operation, permutation, multiplication or composition. Okay, so there is a convention to name these elements of S3. For this we denote the first entry of first element or first function is named as row naught, and we denote this second element as row 1, and this is the element row 2. Okay, and the fourth one is 1 goes to 1 and 3 and 2 are interchanged. So these permutation is represented by the symbol mu1, and this is mu2 and this is mu3. Okay, so this is because this S3 this S3 can be written as the elements row naught, row 1, row 2, row 3, row 2, mu1, mu2, mu3. So these are the 6 elements of S3. Okay, so you can easily evaluate the group table of this S3. So that is obtained by evaluating the multiplication between the elements of this S3. So we first of all we can draw the group table. This is row naught, row 1, row 2, mu1, mu2, mu3. Here we have row 1, row naught, row 1, row 2, mu1, mu2, mu3. Then this is the composition. Operation is the composition. So when you operate row naught and row naught, we can get row naught because we know that this row naught is a identity element. So when we apply when we operate any of these elements with row naught, you can get those elements itself. So that is row naught, row 1, row 2, mu1, mu2 and mu3. Here we have row 1, row 2, because row 2 row naught is row 2 itself, mu1, mu2, mu3. So this is because this row naught can act as identity in this group. Okay, so next we have to evaluate row 1, row 1. Okay, so what is row 1, row 1? Row 1 is evaluated using row 1 is evaluated using this is 1, 2, 3. Row 1 is 2, 3, 1. Okay, and again 1, 2, 3, 2, 3, 1. In order to multiply this, we need to assign images for 1, 2, 3 again. So that is obtained by looking into the image of 1 in this, 1 goes to here, and that 2 goes to 3 here. So ultimately 1 goes to 3 here. And the image of 2 is first of all we can observe 2 goes to 3 here, and that 3 goes to 1 here. So this is 1. So the image of this image of 2 is 1. And in order to get the image of 3, first of all look into this image of 3 in this. 3 goes to 1 and 1 goes to 2. So that is this one. Okay, 1, 3, 1 goes to 3, 2 goes to 1, 3 goes to 2. Okay, and we observe this nomenclature, we can say that this is nothing but our row 2. Okay, row 2 is 1 goes to 3, 2 goes to 1, 3 goes to 2. So you can write it as row 2. Then you can write row 1, row 1 is row 2 itself. Okay, in a similar fashion you can evaluate row 1, row 2. Okay, what is row 1, row 2? Row 1, row 2 is evaluated using 1, 2, 3 here, and row 1 is 2, 3, 1. And what is row 2? Row 2 is 1, 2, 3, and row 2 is this one, 3, 1, 2. Okay, when you evaluate this product, then you can get 1, 2, 3. 1 is mapped to 3 here, and that 3 is mapped to 1. So 1 goes to 1. 2 goes to 1 here, and that 1 goes to 2 here, so 2 goes to 2. 3 goes to 2 here, and 2 goes to 3 here, so 3 goes to 3. So from this you can say that this is row naught. Okay, so row 1, row 2 will give a row naught. So you can consider this row 2 is the inverse of row 1. Okay, or vice versa, row 1 is the inverse of row 2. Now you can easily evaluate this row 2, row 1. Whenever row 1, row 2 is identity, then row 2, this row 2 can act as inverse, then row 2, row 1 is also identity. Therefore we can fill up with row naught here. And what is row 2, row 2? Okay, that can be evaluated using the same technique. Then you will get row 2, row 2 will be row 1. Okay, so in the similar fashion you can evaluate all the product using these elements of S3. Then you can fill up all these boxes as this. Then one thing you should remember is this 1, 2, 3 is irrelevant, because if you have you can take A as this A, B, C. Instead of taking 1, 2, 3, we can take A, B, C, and then the same S3 can be represented using this A, B, C. Okay, using, instead of writing A 1, 2, 3, we write A, B, C, and A, B, C is mapped to A, B, C itself. This is the first element, and then still we will call this element as our row naught. Okay, and similarly A, B, C, and this is B, C, A. Instead of taking 1, 2, 3 here, we write A, B, C, and the corresponding images are like this. Then this is denoted as row 1, and this A, B, C can be written as C, A, B, and this is denoted as row 2, and A, B, C, A, C, B, this is our mu1, and we have A, B, C, this is C, B, A, and this is our mu2. Finally A, B, C, B, A, C, this is our mu3. So this there are several representations for this S3. Even though these are distinct symbols, we call this is S3 itself. Okay, that's why we take this common name, row naught, row 1, row 2, mu1, mu2, mu3. What would be the symbols? There is irrelevant of considering symbols like this. So we write, or we consider S3 as the S3 consisting of 6 functions called row naught, row 1, row 2, mu1, mu2, mu3. Okay, so there is no point of considering these symbols again. Now this is the simplest representation of S3 again. Now why we call this a row naught, row 1, row 2 as this is because S3, these functions are, or these functions can be obtained from some symmetry of the of a rectangle. So if we consider an equilateral rectangle and triangle, equilateral triangle, one and name its vertices as 1, 2, 3, then if you rotate this through 120 degree. Okay, this 120 is obtained from this 360 by 3, because this rectangle, this triangle has 3 vertices. We can get the angle 360 2 pi by 3, that is 120 degree. When you rotate this 120 degree, you will get identity triangle with vertices like this. So this defines a function. Okay, using this 120 degree rotation, you will get a map. This 1 is mapped to 2. When you rotate this, you can get identity, and we place it over this triangle again. Then 1 is mapped to 2, and 3 is mapped to 1, and you can see this 3 here. this defines a function 1 goes to 2 and 2 goes to this 3 and 3 goes to 1. Okay, that means that is nothing but 1 2 3, 1 goes to 2, 2 goes to 3, 3 goes to 1. Okay, so this will give the first rotation. Okay, that's why this is represented by row 1. Similarly, if you perform a 240-degree rotation, you can see 3 over here. Instead of in the place of 1, you can see 3 here. So that defines another function 1 2 3, and 1 in the place of 1 you can see 3, and at the place of 2 you can see 1, and at the place of 3 you can see 2. Okay, so this is our row 2. Okay, so that is due to the second rotation, that's why we call it as row 2. Similarly, if you consider 0-degree rotation, so then you will get the same triangle over here. Then that will result the function 1 goes to 1, 2 goes to 3 goes to 3. So 0-degree rotation is denoted by row 0. That's why we call these functions or permutations as row 0, row 1, row 2. Similarly, when you consider the another symmetry of the same triangle, if you consider the equilateral triangle here, and if you have this is 1 2 3, and if you consider a perpendicular bisector passing through this one of the side 2 3, then you can reflect this. Okay, so suppose this is a mirror, then you can see 3 here by the reflection of this mirror, and this is 2 here, and one can be seen at this same place. So this results a function 1 2 3, and this defines 1 is mapped to 1, and 2 is mapped to 3, and 3 is mapped to 2. Okay, so this is nothing but or this defines a function like this. Okay, so this symmetry will give a function using this perpendicular bisector. That's what we called mu1. Okay, similarly you can consider the perpendicular bisector of this side passing through the other vertex. Okay, 2. Okay, then that will give the function or the permutation due to this perpendicular bisector fixes 2. That means 2 is mapped to 2, and that interchanges this 1 and 3. Okay, so you can write 3 here and 1 here. So that is named as mu2. Similarly, you can consider one more, that will give mu3. Okay, so this is the cause of the nomenclature as rho 0, rho 1, rho 2, mu1, mu2, mu3. So this S3 is also called, or S3 is also denoted by D3. What is D3? D3 is the symmetries of or permutations obtained using the symmetries of this equilateral triangle. Okay, so this D3 is the permutations obtained from the symmetries of or permutations due to the symmetries of equilateral triangle. Okay, equilateral triangle. So this S3 is or S3 has another representation as D3. In a similar fashion, you can consider D4 also. So this is one of the important examples of permutation groups. And next we can consider the symmetries of rectangle in the similar fashion. If you symmetries of square in the similar fashion. So when you consider the square and named its vertices as 1 2 3 4 like this, and since this square has 4 vertices, and we consider the angle 2 pi by 4, that will give 90 degree. Okay, or this is pi by 2. When you rotate this square through pi by 2 degree, okay, that is 90 degree, then you will get the same or identical square like this, and you can see the vertex 2 over here, and 1 is here, 3 is here, and 4 is here. Okay, so this using this rotation you can define a new 1 1 1 2 function using the vertices. If we if this square has 4 vertices, you can consider vertices 1 2 3 4, and at the place of 1 now you can see 2, so this 1 is mapped to 2, and at the place of 2 you can see this 3, So 2 is mapped to 3, and at the place of 3 you can see 4th vertex, and at the 4th vertex you can see the first vertex. Okay, here the first vertex. So this 4 is mapped to 1. So this defines a 1 1 or 2 functions from a set of 4 elements to itself. Okay, and we call this as the row 1. This row 1 is an element of D4. Okay, what is D4? D4 is the permutations due to the symmetries of square. That means regular polygon with 4 sides. Okay, so this is row 1. Similarly, if you consider the rotation through 180 degree, that is 2 times this pi by 2, then you will get another 1 1 or 2 function, 1 2 3 4, and at the place of 1 you can see 3 instead of 2, you can see 3 if we rotate this in 180 degree. So then that will be 1 goes to 3, and at the place of 2 you can see 4, and at the place of 3 you can see 1, and at the place of 4 you can see 2. Okay, so this is named as row 2, that is the second rotation, and this is also an element of D4. That is the same thing, the permutations due to the symmetries of square. And if you consider 270 degree, then you will get the third one, that is 1 2 3 4, and at the place of 1 you can see this 4, and at the place 2 we have 1, and this is here is 2 and 3. Okay, and this is called third rotation. Okay, that is row 3. Again, the fourth rotation is 360 degree, that is equivalent to 0 degree. Then if you rotate 360 degree or 0 degree, you at the place of 1 you can see 1, here 2, we have 3, we have 4 here. Then this is called 0 degree rotation. Instead of taking the 360 degree rotation, we can consider it as a 0 degree rotation. So this forms this is due to the rotational symmetry of a square. Okay, in the similar fashion you can consider the perpendicular bisector symmetry of the same square. That is, when you consider the perpendicular bisector like this, then if this perpendicular bisector is a mirror, then that reflects this one over here, and 2 is here, this is 1 here, and 2 is here, and at the place of 3 you can see 4, and at the place of 4 you can see 3. Okay, again this defines a new permutation 1 2 3 4, and 1 is mapped to 2, and 2 is mapped to 1, and 3 and 4 are interchanged. Then this is denoted by mu1. Okay, this is due to the permutation is due to the perpendicular bisector of these two sides. Then this is also an element of this D4. Okay, so this is named as mu1, and it is an element of D4. Okay, similarly, if you consider the another perpendicular bisector of other two sides, then that reflects these two elements. Okay, so that means 1 2 3 4, at the place of 1 you can see 4, at the place of 4 you can see 1, and at the place of 2 you can see 3, and 3 is mapped to 2. Okay, so this is called mu2. Okay, and this is denoted by mu2, and this is an element of D4 again, because this is due to the symmetries of this square again. Okay, another symmetry of the square is due to the diagonals. Okay, if you consider the diagonal, this diagonal passing through 2 and 4, then you can define a new function 1 2 3 4 using this symmetry. If this is a mirror, then this 3 and 1 are interchanged. Then at the place of 3 there is 1, and at the place of 1 you have 3 here, and 2 and 4 are fixed. Okay, and this is called or this is named as or denoted as delta 1. Okay, this is this delta 1 is because of this permutation is due to the diagonal. Okay, so this is delta 1. Similarly, you can consider other diagonal passing through this 1 and 3, that will give the function 1 goes 1 2 3 4, and 1 and 3 are fixed. Okay, so that diagonal reflects this 2 and 4, so you can see 4 here and 2 here. Okay, and this is denoted as row 2, which is also an element of d4. So these 8 elements, row 0, row 1, row 2, row 3, mu1, mu2, and delta 1, delta 2. So these constitute the a group of symmetries of square or a regular polygon with 4 sides. Those elements are row 0, row 1, row 2, or row 3, then mu1, mu2, then we have delta 1, delta 2. Okay, so these 8 elements are the elements form a group with respect to or under the binary operation composition. Okay, anyway, these are all elements of, or this d4 is a subset of s4, because s4 consists of all permutations from a set of 4 symbols to itself. Okay, so this d4 all the elements of this d4 is a are the functions from set with 4 elements to itself. So you can consider d4 as a subset of S4, and with the same operation of S4, this D4 form a group, then this D4 can be considered as a subgroup of S4. Okay, and this D4, those D3, D4 are you can consider the groups with any n-gun, regular polygon. So those are denoted by dn. If that polygon has n sides, then using the symmetries of that n-gun with regular n-gun, then that is denoted by dn. This is called dihedral group. Dihedral group of n symbols. Okay, obviously this dn is always a subgroup of Sn. Okay, in general. So d3 is discussed, and d4 d3 and d4 are discussed. D3 is same as s3, so d3 and s3 are the same groups, and d4 and s4 are different, because s4 contains 24 elements, 4 factorial elements. At the same time, this d4 contains only 8 elements. Okay, so these are two important subgroups or important groups, or groups consisting of permutations.